Hi, welcome to this new tutorial of our deep learning for geospatial data analysis series. In this tutorial, we'll set up our environment. We will understand the building blocks of deep learning and finish by building a simple convolutional neural network model for image classification. So let's start with the setup. We'll start by importing the important libraries and tools for building and training the deep learning model. So first here we are going to import the NumPy library, so which is fundamental for numerical operations and array manipulations. So this is commonly used in data pre-processing. Okay, next I will import the matplotlib .pyplot module. So this is important for visualizing data, including the images, the learning curves, and if we have evaluation matrix, like confusion matrices. Next, we will load the TensorFlow library here. So an end-to-end open source platform for building and training machine learning and deep learning models. So we will use the TensorFlow dataset here, this module. So in order to get access to pre-process the datasets like the Eurosat, which we are going to use later. So this makes it easy to download and use common datasets directly in TensorFlow. Right, next we will define the neural network by importing the sequential API from the TensorFlow Keras models. So this allows for stacking the layers in a linear manner. So the layers themselves, that is the dense, which is fully connected, and then the conv 2D, this is convolutional, and then the max pooling, which is for downsampling, and then flatten, which is flattening multidimensional arrays into a vector. So these are brought through the TensorFlow Keras layers module. So remember, the layers are the core building blocks for constructing models like the convolutional neural networks. In order to visualize the architecture of the model, we are going to use the plot model module, which is from the TensorFlow Keras utils module. So this function is very important because we can generate diagrams showing the structure of the model, including the input or output shapes and the flow of the data through the layers. Right, if we want to construct a confusion matrix, we can use the scikit-learn matrix to do that. Right, so for deep learning, we need a lot of understanding of mathematical structures such as scalar, vectors, matrices, and tensors. So these form the backbone of how data is represented and processed. So let's start by just defining the scalar. So remember, in the previous tutorial, we said a scalar is just a single numerical value. So for example, 5 here. We are going to print it, and then you see. Next, we have a vector, which is just a one-dimensional NumPy array. So this just represents a list of numbers. So this is often used to describe the features or pixel intensities, for example, in an image. And then we will create a matrix just to show a two-dimensional array. So again, this can represent a grayscale image. And then following that, we generate a tensor using the np.random.rand here, this function. So this is going to produce a three-dimensional array with random values. So tensors are just the generalization of scalars, vectors, and matrices. Remember, we said that these are very essential for representing multi-channel images. For example, the RGB that we use for remote sensing image processing. Right. Finally, we just want to visualize the matrix and the tensor just for the first channel. Okay, so this is after running the code, this is what we get. So for the scalar, we've printed the scalar number, only a single number, and then the vector, a list of numbers. And here you have the matrix, which is just a 2x2 matrix. And this is the visualization of the matrix. And this is the visualization of the tensor, just for the first channel. Right. Next, we want to look at the convolution operation. So convolution is a fundamental operation in the convolutional neural network model. So remember, in the previous video, we said a convolution is just a sliding operation where a smaller matrix called a kernel, okay, a kernel or filter, is moved across the input image, for example, to detect patterns. Right. So this is very important because it helps the model detect, for example, edges, textures, and patterns. So let's try to visualize a 2D convolution and see how it works on the grayscale image. So this is our grayscale image and this is our kernel. So what are we going to do? We are going to use the NumPy arrays and the scipy.signal functions to simulate the process. So we first start by defining the apply function here. This is a function that we're going to define, and this is going to take in a two-dimensional image array and a convolution kernel, which is also a filter. So this the function uses the convolve2D from scipy to apply the kernel of the image, then computing a weighted sum at each location. So here we have the mode valid argument. This ensures that the kernel is only applied where it fully overlaps with the image. So this results in a smaller output. So next here we have our simple 4x4. So we have 4 rows and 4 columns. Grayscale image, which is defined by the NumPy array. So this could be a pixel intensity ranging, say, from 0 to 9. And we are going to apply a 2x2 kernel or filter here. This kernel is designed to emphasize certain features. For example, what we are going to do is to subtract the bottom right pixel from the top left. Okay, this bottom right from the top left. So this can potentially highlight the diagonal edges. Okay, the convolution here is then applied using the apply convolution function, and then we store the result in this object underscore result. Finally, we are going to visualize the original image and the image after convolution. So after running the operation, the convolution operation, this is what we get. So this is just a simple way to illustrate how the convolution works. Right, so next we just want to define a very simple convolutional neural network architecture. So here we're going to use the Keras sequential API. So we are defining a model which has got two convolutional layers. Here, the model with two convolutional layers, and this is followed by the pooling and then flattening, and then the dense layers. So this is just a very compact but powerful architecture for a satellite image classification. So we are going to look at this later. Right, so we define the simple convolutional neural network architecture using the Keras API, as I've said. So this is on top of TensorFlow. So this module just allows for the sequential class, which allows for linear stacking of the layers. Right, so the first layer that we have here, this is the first layer, is a 2D convolutional layer with 16 filters. So each filter is of size 3 by 3, and it uses the activation function, which is a ReLU. Remember we talked about this yesterday. So this is the rectified linear unit. So this linear unit introduces non-linearity in the model. So this is quite important. So we want to make sure that there is some non-linearity in the model. And the layer also specifies that this is the input shape. So the input shape, this is the image, okay, with height and width of 64 by 64. And this image has got 3 channels. So that is RGB, red, green, and blue. So the purpose of this convolutional 2-dimension is to extract low-level features. For example, the edges and textures are in the image. So following that, we have a max pooling layer. So the max pooling 2D with a 2x2 window. So this is used to downscale the feature maps by taking the maximum value from each 2x2 region. So this is important because it reduces the spatial dimensions and the computational load. So next, there's another convolutional layer with 32 filters. Okay, so this is with 32 filters. And these filters capture the high-level features. Again, the shape and patterns, and the activation is ReLU. Okay. Again, this is followed by another max pooling layer in order to reduce the feature size. Okay, so after the convolution and the pooling operation, we have the flattened layer here. So the flattened layer, which transforms the 2D features, the 2D feature maps into a 1D vector, so that it can be fed into a fully connected layer. Okay, it can be fed in the fully connected layer. So the flattened output, that is the 1D vector, is passed through this dense fully connected layer with 64 units or neurons. And the activation again is ReLU. And this enables the model to combine the length features in a meaningful way. So remember, when we are looking at the convolutional neural network, we think of getting meaningful representation, so that we can get whatever we want to do from the model. Right, then finally we have the output layer. So this is a dense layer with 10 units and and a soft max active action. So this is appropriate for a mode classification problem because the data that we are going to look at later has got 10 classes, the Eurosat dataset. That's why we put here the 10. So 10 represents the 10 lane cover classes. So these are the categories. And then the activation is softmax because here it's going to produce a probability for each class. And then finally we have the mode of summary function here at the end. So this is going to display the detailed summary of the model architecture. So it's going to show us the output of each layer and the number of trainable parameters. So this gives the user a clear overview of the model structure. So if we run this, we are going to get this output. So this is showing the output of each layer and the parameters. Right, as we can see, so this is our result from our convolutional layer, convolutional model, sorry. Right, so what we have here first the Conv2D. So it's showing that we have 16 layers. Okay, 16 layers. And then our shape has been reduced. Remember, our shape was 64 by 64. So it has been reduced to 62 by 62 because we don't have any padding here. And the first convolution 2D layer here has got 448 parameters. Okay, 448 parameters. So how do we come up with these parameters? How is this calculated? So this is simple. Remember, the input channel has got the image has got 3 channels, right? Okay, so it is RGB. So we are simply going to multiply the input channels. So 3 times 3 times 3, and then we add the bias term, and then we apply with the 16 filters. So remember, the first one has got 16 filters. So this is going to get the parameters for the first layers. So the first layer has got about 448 parameters. Again, so what are the parameters? So remember, when we look at the neural network, we have weights and biases. Okay, so the weights are just the values applied to an input image. So this could be the pixel values. So this determine how much influence an input has on the output. Okay. So in a convolutional layer, weights define the filters that detect the edges or texture. And the biases are just offset values that are added to the weighted sum of inputs. So this allows the model to fit patterns even if we have all the inputs as 0. And the none here means that the batch size can be anything. Okay, that means the batch size that the model takes can be anything. Right. So for if we look at the second layer, the max pooling 2D here. So we said this is for downsampling using a 2x2 polling window. So this is going to reduce the size by half, so the size of the image. So our image is 62 by 6, they are reduced by half, so we have a 31 by 31. And then this is the filter. And here we don't have any learnable parameters because we're just reducing. And then when we look at the third layer, the conv2D, the convolution two-dimensional here. So here we have 32. So we have the 32 filters with a kernel of 3 by 3. Remember, we had a kernel of 3 by 3. And our parameters here, we have 4,640. Okay, so again, how do we get this? So we have our the RGB images. So the channels, these are 3 by 3. We multiply 3 by 3 times 16, and then we include the bias, and then we multiply again by the 32 filters. This is going to give us this value. So these are the parameters for the conv2D, the second convolutional 2D layer. And then we again look at the max pooling. Again, this is for downsampling. So as you can see, there's a downsampling that is happening. Okay, so the size is reduced. And then we look at the flatten. So as we say, flattening here is just a conversion of the feature maps to 1D vector. Okay, and we also get this value. So this value is just a multiplication of this. Okay, because we are flattening this, so it's 14 by 14 times 32. This is going to give us 6,272. And then we have our dense layer here. So this is the fully connected layer with we said with the ReLU activation. So this is for high level feature learning. And finally, and this one has got 401,472 parameters. Okay, so this is quite huge. So it's just taking this parameter, this input features, 6,202 input features, multiplied by 64 neurons, and then we add the bias term, that is just plus 64 biases, and then it's going to give us this number. Okay, so these are the parameters. Then finally, we have the final output here, which is the final dense layer. And as I said, this is just showing the number of classes that we have, the number of length classes. And here the parameters that we get is 640. So it's just multiplying these input features, 64 input features, times 10. So this gives us 640. And then if we add a bias of 10, it gives us 650. And then here we see the total parameters that the model is going to use. So these are the trainable parameters. How do we get this trainable parameter, this number? You simply add these parameters, and this is going to give you 407,210 parameters. Right, so I just want you to be familiar with this so that when you build your convolutional neural network, you can learn how to interpret it. Right, so why do the parameters matter for the CNN model? Number one, because they show the model complexity. So if we have more parameters, then we have more capacity to learn complex patterns. And but sometimes there is a risk of overfitting if the model becomes too complex for the data set. So you need to be very careful. And then also parameters are very important for memory or computing cost. So parameters are stored in memory and updated during training. So larger models, which requires billions of parameters, require more computational power. This is just a small model. Right, so this tutorial just concludes what I wanted to show you. That is we showed you the building blocks of for deep learning model, for example, the tensors and the convolutions. And then we finished just by building a simple CNN model for image classification. So in the next tutorial, we are going to build and train a simple model, okay? In fact, based on this model, to classify satellite images from the Euroset dataset. So that's all about this tutorial. So thank you very much for watching. See you in the next one.